much. For the sake of time, we're going to move to the next speaker. Thank you very much, Sam.
Thanks.
Okay, so the next speaker is from UCL, and it's Mariya Mamajiwala, and she's going to talk about the efficient parameter estimation with nonlinear stochastic filtering. So if you're ready, please start. Thank you.
Can you see the screen?
Yes, we can.
Okay. Okay. Hello, everyone. So I'm going to talk briefly about estimating parameters of a dynamical system in the context of data assimilation. So let me start by defining the problem and setting up some notations. So we have a system dynamics represented by this SD here. F is the function of the system states and parameters. So if the parameters were known, this would just be a constant theta. But when they are not known in the DA setting, they are assumed to evolve as Brownian motion as additional states. So we have now a combined state and parameter estimation problem. And this is an important point for this talk because this is where we propose a modification. But let me put a pin in that. So from here on, I will be referring to this equation as the original parameter dynamics. Then we have measurement dynamics. So I have written an algebraic equation, but this could as well be an SD. It doesn't really matter. And finally, we have some measurements available at certain time intervals. So the aim is then to determine the posterior of X and theta, given these measurements in Z. Now, without any loss of generality, we are working with the ensemble Kalman filter. This choice is mainly for convenience, and we should use a DA method that is most suitable for a certain problem. So assuming we start with an initial ensemble for this X and theta, ENKF works in two steps. The step one is to predict, so pass the initial ensemble through the process in parameter dynamics. And then step two, which is the main DA step, we apply this additive correction. So here Z minus HX is sometimes known as innovation because this is where the new information comes in from Z. And K is the gain matrix. It's a function of the predicted states and parameters, predicted observations in HX, and the measurement noise intensity, sigma Z. So coming back to this parameter dynamics, although this is perfectly correct mathematically, its practical implementation is often very inefficient, as there's really no drift associated with this dynamics. So this results in certain issues that are either there is no convergence, especially for the parameters, and if it exists, it's typically slow. The sampling variance associated with this, especially the parameters, is typically large. And also, it becomes increasingly difficult to solve a problem, especially for the parameters, as the problem dimension increases. And if you've noticed, the measurements only play an indirect role in the parameter update. So that is only in the update step of the DA. So motivated by these issues, we propose a way of using measurements directly in the parameter dynamics by introducing a drift term. So I come to the main idea. The idea is to construct a pseudo energy using the available measurements, and then use this energy to define or construct an overdamped Langevin dynamic system. So assuming an energy field is given, this is what overdamped Langevin diffusion looks like. Here, beta is a temperature-like quantity, so it should be positive. And also, it relates to the mobility. So higher temperature means more mobility. And we want to reduce mobility with time as we converge. So it should be a non-increasing sequence. And the process and measurement equations remain unchanged. So now these three equations define the problem. So notice we are basically just changing how the problem is posed. And we'll see how using measurements directly here affects the results. But first, the question is how to define this energy field. So since it's pseudo energy, there are basically infinite ways to define that, but certain points must be kept in mind. So since it's an energy-like quantity, it should be non-negative. And ideally, it should be a unimodal function with a minimum at the desired location. So any convex function should be a good choice. And one possible choice that we are working with is this expression. So if I call this expression inside the exponential as v, which is a squared error-like quantity, this is what the gradient of E looks like. So it has exponential of a squared error. Then it has component-wise errors appropriately multiplied with the partials of h, the measurement function, and also partials of x. So to obtain the partials of x, we simply expand the process dynamics by an implicit Euler-Mariya integration scheme. So this partial of x will basically contain the partial of f. And just for the sake of completeness, so this is what the modified parameter dynamics would look like for this particular choice of energy. Okay, moving to the numerical simulations, we consider the Lorentz 1963 model. It's a three-state, three-parameter system. And this is what a typical response of the system looks like. So it looks like a butterfly and also exhibits the butterfly effect. So because it's a chaotic system, a small change in the initial conditions can cause large changes later on. We use these reference parameter values along with these initial conditions to generate the measurements. So it's for a toy problem. And we are measuring all three states, so x, y, and z, with an intensity of 2. So it's quite large. And for the original parameter dynamics, so we compare the results with the two methods. We assume an intensity of the Brownian motion for the original parameter dynamics as 0.1. I think I went forward 2 slides. Yeah, so these are results for an assimilation frequency of 1. That is, sorry. So we assimilate at every time step. We have parameters on the left and states on the right. And if you look at one of these plots, so the pink plot is the result with the modified parameter dynamics for an ensemble size of 10. And that is compared with the one in green, which is with the original parameter dynamics, the Brownian motion, again for an ensemble size of 10. And just for the sake of understanding the comparison better, I've included 2 more plots, the blue and orange, which are results with the original dynamics, original parameter dynamics for an ensemble size of 100 and 1000. And as you can see, even with 1000 particles, the results with the original dynamics don't compare very well with the modified dynamics. So it plays a big role. And even for the states, we see a better convergence for the states as well, because the states and parameters are coupled. Okay. Right. So now we have some sampling variance plots for the parameters. It's the same problem as before, but we now have an ensemble size of 25. And we formed 100 independent runs with each of the methods. So the original and the modified parameter dynamics. So in each of these plots, the gray plots are the independent runs. Black is the mean of those independent runs, and the red is the true parameter value. And as you can see, the contrast between using the original dynamics and the modified dynamics is pretty sharp. And also there's a bias with the results in the original case. This would most likely go away with a higher ensemble size, but it does not seem to be an issue when using the modified dynamics. Okay. We now have some results for a lower assimilation frequency. So we assimilate every 10th time step. And the original parameter dynamics don't change because it's just Brownian motion. But if you recall, the modified dynamics is a function of the observations. So until a new observation is available, we keep using the same gradient in the Langevin dynamics. And if you look at the free plots by the original dynamics, so the green, blue, and orange, the results don't improve much, even with an increase in the ensemble size, because we now have lesser data available. And this is an important point because we usually won't have much control over how much data is available. So modified dynamics is somehow able to make better use of the data that's available. And even for the states, the comparison between the two methods is even more pronounced than before. So to summarize, we modified the parameter dynamics as a pseudo-Langevin system, which is based on a pseudo energy constructed using the measurements. And we saw that the ensemble size as well as the sampling variance are significantly reduced. And at a small increase in the computational cost, the overall quality of the results is improved. So the increase in computational cost is more than made up for by the improvement in results. And yeah, we saw that the states, convergence of the states also improves as a result of modifying only the parameter dynamics. Finally, for some future directions. So the first thing to look for would be a theoretical convergence analysis. And it's possible to do that using change of measures. So it's possible to at least get a comparison between the two by just using change of measures. And then next, instead of using the Langevin diffusion equation as it is, we could use the stochastically developed version, which is equivalent to the Langevin diffusion honorary Manning manifold. And we used this earlier, in fact, for solving a non-convex optimization problem, but it can be readily applied in the context of DA. Next, we could use the generalized Langevin dynamics. So currently we are using the overdamped Langevin dynamics, and the difference is in the overdamped case, the damping is 0, the acceleration is 0. In the generalized Langevin dynamics, not only there's an acceleration present, but there is a flexibility to use history dependence within this dynamics. And this could be very useful in DA when the data is sparse. And finally, for higher dimensional problems, we could use SGLD or one of its many variants that are available in the literature. That concludes. So these are a few key references, and I thank you all very much for listening.
Thank you very much, Mariya. A very, very interesting talk. On to see, I believe there is one question. I'm not sure it's for the talk. Probably it's not related to your part. So, okay, we just keep looking for that question. Can you just briefly tell us what kind of computing powers do you need for your analysis, and what?
Sorry, yeah. So you mean the increase in the computation due to this?
So for the problems of your primary concern, do you use kind of supercomputers, or you can deal with it easily with any kind?
So currently I've solved only small dimensional problems.
Okay.
But this can readily be applied anywhere parameters need to be estimated using DA.
Mm-hmm. Okay, great. Thank you. You saved us some time. We can